In our last video, we understood about different types of gradients. We understood, till now we talked about deep learning methods, deep learning, what is neural network, how neural network works. We have input layer, output layer, hidden layer, and what is weight or what is bias, how those things are getting worked, what is activation function. We have, during our deep learning, I have given some hint about optimization techniques or optimization functions. So we are going to talk about optimization techniques today in a complete a broader sense. And hello everybody, welcome back to my channel. So let's start on our optimization techniques right now. So we have understood about gradient descent, which is a really important topic as compared to your throughout your overall deep learning concept, right? So what is gradient descent? Gradient descent is a it's a technique or is an algorithm which helps in reducing a loss function, right? Or in short, I can say that we have, when we are moving from input to output layer, right? We have some values, right? Some target values in input, and we are getting some target values in output. So we will get some error part there, right? So error comes into picture when we are reaching at your output layer. So that error part or that error function, which is a loss function or cost function when we're talking about, is needed to be reduced, because we do not want our output or accuracy should be lesser. It should be higher, right? And how to achieve that higher accuracy? By reducing our loss. So my gradient descent is exactly helping to do that, to reduce the loss. And that is again one of the optimization technique, right? Gradient descent or your simple gradient descent is a optimization technique which we have covered already. And we have few more optimization techniques which are really necessary or which takes a greater role in your output layer to handle this weight part or weight updation and how to handle the loss things. Everything it will take care. So let's understand what is optimization technique. So what is optimization technique? So as I mentioned that these are algorithms to train neural network by minimizing their loss function. So when we're talking about loss function, what is a loss function, guys? So we understood about MSE, mean square error, mean absolute error, right? We have binary cross entropy, right? So cross entropy, and we have Gini index. All those things are an error, right? So we know that with that we are understanding what is the error percentage or how much error we are getting. Suppose we have one output like one house price, right, as a target, and whatever we are getting, so that difference we are understanding that's an error part, right? However, here in this case, in case of deep learning, we are all working on weights. So we are understanding that, okay, for this feature, whatever the amount of training or the amount of learning it's needed, based on that my network is assigning weights, right? So all I can say that we are manipulating weights here. The weight is a bigger picture in case of deep learning. So when we are understanding that we have either higher weights or lower weights, we are understanding that that needs to be controlled based on the amount of error which we are going to get or which needs to be reduced. So that thing is getting handled by your optimization techniques. And from how it is handling, it is getting handled through your back propagation, because back propagation is the way with which you are handling our weights, right? There is another way with which we can understand, or I can say we have another definition. So just the way I mentioned, it is very simple. It's a difference between predicted output and actual output, right? Through iterative updates to networks, weights and bias. So guys, why we're adding bias? Any idea about it? So guys, we know, right? I mean, we have activation function, we have, we have like this, right? W, of F equal to Wx plus B, right? W final. So this is my bias part, right? So my bias part is taking a great control to handle my activation function. So without my bias, just imagine that there is a line, right? We have a line function y equal to mx plus c. So when without c or without c here is what? We have a bias, or we can say that's an intercept, right? So without that, our line will always try to reach out towards your origin, right? However, in case of your bias or in case of your intercept, it clearly shifts from the origin and it intercepts through two lines, right? And that's where we are, or I can say that we are, shifting from your linearity, correct? Here, in case of bias, it helps my activation function to activate my proper neurons. So if somebody will ask an interview, what is the role of bias? You can clearly say that with bias, we can achieve, which neurons should be activated. Even though you do not have a proper weight, the bias can take that part and it can give you a final output. So WF is a final, right? So it's going to give a final weight. Okay, this should be my weight. It won't be completely zero. So bias is taking a great role in case of handling your activation function. Now I will show you one of the image or one of the drawing where we can just understand, okay, how my optimization function as compared to your gradient descent, how it is getting used. Because my gradient descent, it's just normal zigzag motion, and we have that is the only way, or that is the only path it follows, right? So optimization techniques is one step above your gradient descent, and we will see from this drawing or from this image. Let's see that. So in this image or drawing, what I have drawn, right, we have inputs, right? We have inputs. We have, this is my hidden neurons, and this is my output, correct? So when, you can see that all my inputs, we are assigning weights, and my hidden layer neurons consists of my weight function or f of x and the activation function. So it's a combination of f of x plus activation function. And I'm not going to say that my output layer cannot handle my activation function. It can have my activation function. It's based on the requirements. However, you can see that my output neuron should have one error function plus my optimizer, right? Because from here, weight updation is happening, correct? Weight updation is happening in my back propagation. So this is my overall thing. So why I have drawn this, I just wanted to identify, or I wanted to detect that, okay, at which portion my optimizer comes up. Even in code part, if while you create your own architecture, right? So there we will, you are creating your input layer, you are creating your hidden layer, and input layer and hidden layer, we will be having this activation like relu and all will come. And when you are compiling your code or your model, so there you are creating a model, right? You are creating a neural network for a model. So their training happens. But when you go ahead, move ahead for compiling, at that time, this optimizer you need to pass. So either you can just pass, we have different types. I will, touch base. But however, we have, one of the famous one, which is nothing but Adam, which you are using frequently in while creating your own neural networks. So we'll cover that. And in this image, I have shown one comparison, like even though gradient descent is a good optimizer, but it is not an effective optimizer, I can say, because you can see that Adam is going to be faster as compared to your gradient descent, because my gradient descent takes different oscillations, right? Like just imagine that a ball is flowing, or when you're throwing a ball from your hill and it glides over the surface, it takes different motions at that time. It's not easy to come down to the ground. So that motion, in one way it is slower, in one way it is faster. So gradient descent, it is slower, Adam, it is faster. So that is the overall image, or that is the overall concept I have shown it here. Now we will understand what are the different gradient, different optimization techniques. So we understood about gradient descent. We understood about, or this again, I can say that it is a batch gradient descent, right? Then we have stochastic gradient descent, where it takes one input and it understands the loss of it. Then we have mini batch gradient descent. Now I want speed up of my gradients, right? So for that we have, for speeding up, we have momentum based methods, right? So when there is a term called momentum, that means I can say my gradients are getting momentum to act faster, right? Like you can understand in that way, because we have a momentum based methods. And what is the significance of this? Because our standard SGD, or standard gradient descent, can zigzag and get stuck. Where it will stuck? Just imagine that your ball is gliding down from hill, and somewhere it found this hole, so it's stuck there. Or it's a, I cannot say it's a complete hole, but yeah, I mean there is a dip and there is a, a bulge area, there is a dip area. So from that dip area, it's stuck. So that's nothing but a local minima, right? So it has, like it's getting stuck in your local minima, which we do not want. We want our momentum should be there throughout. It should not stop anywhere, because that's the place where your learning is happening, right? And you should not want your learning to be stopped. So we have momentum comes into picture. So what my momentum is doing, it adds a fraction of previous update, or I can say it's taking the previous velocity and it's updating your current one based on that, and it's updating to the current one, right? It's taking the previous update and it's updating the current one. So that is how my momentum works. And throughout this momentum, it gains inertia of a ball. Just imagine that it's rolling down. So throughout this, it gains the inertia while rolling down to a hill. So this is an example, right? Throughout that activity, it gains inertia while it's rolling down a hill. That's it. And we have various types. One is nesterov accelerated gradient, which is called as NAG. It is called as NAG. And when I'm talking about NAG, just a form of momentum based. What it does, it looks ahead to where next step will be before calculating gradient. Or Nesterov accelerated gradient. So so here I am just covering what are the different types, right? I'm going to take each one, and I'm going to explain the methods, the mathematics behind it, and everything in our upcoming videos. But let's understand what are the different types we have right now. Then we have one more type, which is called adaptive learning rate. So we know one is our gradient descent, and to overcome or to tackle my speed of gradient descent, we have momentum based optimization methods. Now we have one more thing, right? When I am updating my gradients, or when I'm getting my gradients, we have one more thing. We have a learning rate. So we know that if you are using small learning rate, the learning is slower. If you are using higher learning rate, or that number I'm talking about, so that number, if you are using higher, it will take larger step and it completes the convergence. We do not want that part. We want the learning rate should be dynamic. It should not be static. And we are going to achieve that with our optimization techniques. So we have various optimization techniques to handle my learning rate. We will understand that. So what I have told already, so instead of single learning rate, which we have implemented till now, we have used single learning rate, right? We have used 0.1 or 0.5 or 0.9. 0.9 is a very higher one. Either we can use 0.1 or 0.5 we have used till now. So 0.1 is the most frequently used, because that will make your learning process good, because you want your model should learn things, right? So most of the times, or till now, we have used single learning rate, right, as a whole. And what is happening with these methods, with adaptive learning rate, change learning rate for each weight individually based on how frequently it is updated. So we know W new equal to W old minus delta into dl by dw. We know this, right? So each time this learning rate is going to be changed based on your weight. So that's what I am saying, that with the adaptive learning rate, this is going to happen. So we have various types of adaptive learning rates. One is your Adagrad, So what my Adagrad is doing, it slows down, right? I mean, it slows down learning for frequently updated parameters, but it accelerates at the same time those updated rarely. So what my Adagrad is doing, so throughout this, it's my learning rate is helping to update your weights. So what it will do, the weights which are frequently updating, right, throughout this process, because when we are creating your, neurons, there is an option, okay, when you're creating your architecture, you will pass the number of neurons. So just imagine that you have a lot of neurons, we have that complex process, and throughout that, your weights are getting updated. And those weights are getting updated with the help of even learning rate, because uh, my weights are the biggest character here, which are helping your model to learn, right? So when it is happening, like when my Adagrad is happening, at the time the frequently updated weights are like it slows down their learning, and it gives importance to the one which are not frequently updating. That means it wants all the weights to learn properly. They do not want to miss anything. That's why this Adagrad is coming into picture. And it has one loophole at the same time. That learning rate can be too small. So just imagine that you are not updating the frequently updated weights properly. That means you at that place you are using very small learning rate, right? Because you do not want to update them, because you cannot make them zero. However, you will use 0.0001 or 0.000001 like that. So with that, what is happening? Your learning rate can be smaller in those places, right? So that can be one of the loophole. To handle that, we have another type, which is nothing but your RMSprop. You must have heard about this already. So what it does, it solves Adagrad's limitation. So we have a limitation there that even though it is doing a good work, but it lacks in your learning rate, which can be smaller, very smaller number. Adagrad's limitations. And how it is handling that limitation? It exponentially averaging recent squared gradients. So what it is doing, it is squaring up the gradients and it is taking the exponential average. And with this, it prevents learning rate from vanishing, right? Because we all know with when you're squaring up something, then that number is becoming a little bit bigger and it's visible, right, at the same time. So these are the different types we have. Then the third one is going to be Adam. It's very important, guys. Most frequently asked question, right? So let's understand this. So what is my Adam? Adam is a mixture of, or I can say that what is the full form of Adam first of all? It's adaptive moment estimation. Right? Adaptive moment estimation. So we know that we are using Adam in most of the cases, and It's a great and popular optimizer, right? Then all it has, like how it works, it's just a combination of momentum, that means it gives direction to my neurons, and RMSprop, or I can say adaptive speed. Right, so it's a momentum plus RMSprop combination, and it works well with your default settings as well, right? So now we will understand one example on how my optimizer works, or how it changes the gradients frequently to achieve your convergence. We'll see that, and we have seen one similar example in your gradient descent, right? We will see the same thing here. What is the function, or what is the issue it is handling? My optimization technique is handling your minimizing of your loss function, right? So minimizing of loss function, that is my goal here, right? So just take one loss function in that case, right? We have theta minus 3 square, so this is my loss function I have taken. So what my optimizer will look, it will look for gradients. So we need to find gradients, right? What is the formula? dj by d theta, just 2 into theta minus 3. So this is my gradient, right? Next, we will take one by one, and before we will start, we all know that at theta equal to 3, my gradient equal to 0, right? That means here my learning stops, here my model learns finally. So what it will do, so the point it will start and it will take the step. That's how step, right? That's where we are taking learning rate. Learning rate is nothing but your step here. So it takes different steps to reach out to your 3, right? Because that's your goal. That's the goal of my gradient. It will reach there, so the learning stops for that neuron, right? So at theta equal to 3, we all know my gradient equal to 0. So it will start, let's start at theta equal to 8. So it will start at 8. So with my 8, what will be my gradient? We all know 2 into theta minus 3. So my gradient I'm getting 10, which is my positive number, right? That means it's here, right? Somewhere here. It will start here. It will come here, right? Then after that, it takes like this. So just imagine that this is your scale. So this is your scale, right? And this is your 3. So it starts from 10, it comes till 3. But let's see that. It takes the steps in that way only, guys, right? And we all know that my learning rate is nothing but your step size, right? Now we will update parameters. So what will be my formula for that? We know theta learning rate, right? Which is dj by d theta, right? Theta new equal to theta old. Let me just theta new. So we have theta old. So with that, I will get 8 minus 0.1 into 10, which is 7. So my 8 becomes 7 at this point, right? Then it will look for a new iteration. It has updated that. Then it will take again my 7. Then it will calculate dj by d theta, which I'm getting 2 into 7 minus 3, I'm getting 8. Then at theta equal to 7, I need to update my parameters, right? So it's going to be 7 minus 0.1 into 8, which I'm getting 6.2. So I got from 7, it becomes 6.2, right? So just imagine that, just the way I told, that it needs to convert. So it will take different steps. So just, I have calculated already this. So I'm just summarizing it. My 8 becomes 7, right? At 2, my 7 becomes 6.2. At 3, my 6.2 will become 5.56. Just like that, it will converge. 5.56 will become 5.048, right? So it will start going closer to 3, right? And that helps. That's how it completes its learning. And we all know, right, optimizer helps in fast convergence. That's why we are using optimizers, right? And we have completed our discussions on our optimization techniques and all, and we will understand each one, like what is momentum based, how it works and all, in our upcoming video. And like that, we have few more, so we will understand them in our upcoming video. And please subscribe, like, share your comments, share your feedback, share this channel link to all your friends and near ones. If any of these contents are making sense to you, if this helps to to grow in your career. And we will meet in our next video, guys. Thank you. Bye. Take care. And do not forget to hit the bell icon while subscribing. That's the most important. So we'll meet. Thank you.